Hi there. In this video, I'm going to walk you through an example that illustrates why choosing to invest in a channel with a higher ROAS is not necessarily the best idea. So you see in front of you a spreadsheet. This is going to explain this entire scenario. So we have in this situation two channels, channel one and channel two, and we're going to look at why this is the case. So let's look at the metrics that we've chosen. So it's simple spend revenue, and then we have calculated a metric called marginal return. And we also have the ROAS that's been calculated. Now, this could potentially also be POAS or profit over ad spend. So, that could also happen. I mean, you could also have profit here instead of revenue, and this is not going to actually make a big difference. So let's look at what we have in terms of the spend. So this is a dummy data set, of course, but you can use yours and see if this is the case. So this is a two-channel explanation. Um, if it becomes more than two channels, then it can be a little bit more difficult, but the gist and the approach kind of remains the same. So, so we obviously start at zero spends, and then we move on towards 1 million. So everything here in this example is in $1 million. And as you can see, for each of the channels, it varies from 0 to 8 million. Now, for each of the corresponding spends for the channels, we have the respective channel revenues. So channel one, for instance, when it spends $1 million, has a revenue of 6. Channel two has a revenue of 3. Channel 2 has 9, then it has 5.8, so on and so forth. Now, we are concerned about one point. That's of course going to make our assumptions, or rather make our approach easier, because we want to understand at a specific data point what is going to be the decision, whether or not to invest the next $1 million in channel one or channel two, right? So yeah, let's look at what's happening at $3 million of ad spend. This, by the way, is basically the plot for the data points, but as we'll also see that this corresponds very much to what's called a media curve or a response curve. We're going to come to that a little bit later, but for now, just imagine that this is just the plot of the data points that we've seen above, which it is actually also. And you can see that for 3 million ad spend, this is going to be the ROAS, right? So you can divide the revenue by the spend for each of the channels. And we've seen above that at 3 million ad spend, the ROAS is 3.5 for channel one and 2.6 for channel two. So this is the critical point. You might think that, okay, we are at a position of 3 million ad spend. And now I think, we have the data to prove that the ROAS is better in channel one. So why not put more money into channel one? Because then it means that it's going to do better and it's going to give us more revenue, right? Just wait. So this is where we do what's called the marginal return calculation. The marginal return calculation is actually pretty simple, as you can see here. So it is simply C4 minus C3, which is this minus this, and then you divide it by the corresponding ratio or the corresponding difference of the spend for that channel. So this is going to be this minus this. So that's how it progresses, right? So it's the difference of revenue, and taken over or as a ratio of the difference of spend. So that's basically the marginal return. And as you can see at 3 million ad spend, the marginal return of channel one is actually lesser, right, than the marginal return of channel two. So that is the critical question. So you have a ROAS which is higher, but you have a marginal return which is lower. And here's what goes. If you choose to go with the higher ROAS channel, it's actually going to result in a lower revenue, lower total revenue than it would have been if you had gone with the channel with a higher marginal returns. So let's actually look at the scenario here. It's easy to calculate manually also, and you can see what I've done. So scenario one is where you add $1 million more spent to the channel one at 3 million ad spend. The total spend that becomes 7, right? Because two channels both are spending $3 million, and you add one more. So this is the situation where you are adding a net more spend. And the scenario two, and then the total revenue in that case, if you actually look at this here, so if you are now spending $4 million instead of yeah, so you're spending $4 million in channel one and $3 million in channel two. So your total revenue then becomes this one plus this one, right? So it's 11 plus 7.8. So that's why it becomes 18.8. In the scenario two, where you add $1 million to channel two at 3 million spend, which means that you have a spend of again $7 million, and then you are now taking this revenue and revenue from here, right? And that becomes a total revenue of 20.3, right? So hope you're understanding what I'm doing here. This is corresponding to this, and this is corresponding to this one. Okay. So you can see that in this scenario, or in this case where you're adding a net additional amount of $1 million, there's actually more revenue to be obtained or generated if you are going with the channel which has a higher marginal return. Okay, it's simple logic because this is like per unit addition of dollars, you get better returns at that point, from that point at least. And you have to check that at every stage and then decide. It depends on the model, it depends on the curve, and therefore that is going to determine your forecasting from any point that you're making in the future. And this is another case where you add $3 million spend of each channel, add $3 million spend of each channel by decreasing $1 million from channel one and reinvesting in channel two. Okay. So in that case, what happens is that you're taking away $1 million spend and you're reinvesting in channel two. So in that case, what's happening is it becomes $2 million in channel one, and then it becomes $4 million, right? So instead of $6 million being equally distributed between the two channels, you have $2 million from channel one, $4 million from channel two, and then you can see then you're adding up this revenue, and then you're adding up this revenue, which is 18.8 in total. And previously you had 18.3. Okay, so there you go. That's the difference. So it's still it's 0.5 in the difference. So essentially what's happening is when you are decreasing from 10.4, when you're decreasing the spend in channel one from 1 million to, by $1 million from 3 to 2, then it's decreasing from 10.5 to 9, which is 1.5 decrease. But you're reinvesting that in channel two, so you're increasing it from 7.8 to 9.8. So it's decreasing in channel one by 1.5, but it's increasing in channel two by $2 million. So the net gain by reshuffling the budget from channel one to two is actually $2 million. Now, strictly speaking, this is an optimization problem in mathematical parlance because you have to optimize total revenue on the basis of a couple of inputs here, which is several inputs here, which is the spend levels and also the marginal returns. And then you can sort of vary the spend distribution across between the channels and see what is the optimal level of spend distribution. So this is an optimization problem. Uh, I have spoken about this past in some of my videos in the past, but I'm going to do that in the future. But for now, the important point to understand here, no matter what approach you take, there's several approaches you can take to come or to arrive at this decision of which channel or what is the distribution of the spends across channels. But the point to understand is that it's not necessarily the one with the best ROAS that wins. Okay. I mean, in reality, sometimes it does win in the sense of actually getting the budget allocation, but it's the marginal returns that should matter more. Now let's take a closer look at this graph. This graph here, seeing here, is actually a plot of this graph. This has been generated using Python. But that's besides the point. What's more important to understand is that it represents the important point that I was making, that when you go from 3 to 4, the revenue, total revenue, or revenue for this channel increases by 2 million, it decreases by 1.5 million, um, as it moves from 3 to 2, right? But the net gain, the total revenue is increasing by 0.5 million. Now, the point is, like I said, this is a plot of this data set between the spend values and the revenue values. But this is actually also, the way this data set has been generated deliberately is to showcase two curves which are called diminishing return curves. Now, diminishing returns, you must have heard of it. As you spend more, there tends to be a saturating effect, not necessarily a saturation, but there tends to be sort of a tapering off of the revenue, the response that is. So revenue is the response here. That's why it's called a response curve. What's the response of the model with increasing ad spend in this case? And as you can see, for both of them, there's the diminishing returns tendency, but this shows a much stronger saturation effect, the channel one, which is why, if you actually look at the values also, you'll see that it's reaching a saturation point much faster, right? While this continues to have an increasing effect, there's a slowdown in the growth, clearly, as you can see, but it still continues to have some growth as the spend increases. So this is what is basically a response curve. And now this, so in a real scenario, what will happen with you is that you're going to have a historical data set, right? So you will have a lot of data points, channel data points. You will have data as to how the channels have performed, but you will have to create a model, right? So that you can predict the future. Now you can do this in many ways. You can use regression models. You can use so many other approaches. I'm going to talk about a few of those. But you also have to then cross-check whether or not that model is correctly fitting the model or not, whether or not model fits the data set and vice versa. So that's called curve fitting or model fitting. And let's actually look at this example here. So you see there are three models which are actually tested for curve fitting this data set. Okay. And you will see that this is the channel one data, the blue markers here. Those are the data points. They have been distributed. They are distributed in this fashion. Then you have the linear model. Then you have the diminishing returns model, which is this orange curve line, and then the red curve line stands for the saturation model. As you can see that the diminishing returns and saturation models both have a very strong, and they are very similar, by the way. It's just that the saturation effect is stronger, as the name suggests, in the saturation model. And so they fit very, very closely, while the linear model does not. Just this has been created just to give you an indication of the nature of the problem of the approach at hand here. So I've created a detailed notion guide. This notion guide is going to talk about the types of response curve models. And as you can see here, this is also a very nice example. There's a power law model. There is the Michaelis-Menten one, the negative exponential. I've explained some of these below. Again, similarly, advertising units. This is advertising units, but it could easily be ad spend as well in the x-axis. And response is whatever you are measuring in terms of response, whether it's revenue or profit. Now, I'll just come one by one to some of the models that I've listed down here. So there's the linear response model, as you can see, where R is the revenue, S is the ad spend. This has been throughout the notation that has been used. Then marginal revenue per unit of ad spend is your A, right? So suppose if B is 0, how much does the revenue increase for every unit of ad spend? And that is your A. Okay, that's the common coefficient in any linear equation. And then the base revenue when S is 0, what does R equal to? That's your B. So that's a simple linear response model, which in this case is your dotted line here. Okay. Then you also have the diminishing returns model, which is the Michaelis-Menten model, for instance. And here it captures the diminishing returns where the incremental spend results in smaller increases in revenue. Right. Again, something you must be familiar with, even if not so much with the mathematical equation. But again, R and S, they stand for revenue and spend respectively. The maximum revenue as S tends to infinity is equal to A. And you can see here easily, and I think this is important. You have to become a little bit familiar and comfortable with some equations. You know, depending on your background, you must be aware of them or very familiar with them already. And most of this is actually very high school math. This is not necessarily very advanced mathematics also. But if you're somewhat familiar with equations or you're at least comfortable with them, then it should be easier. If you're not, I suggest that you start getting a bit comfortable. Then this entire process of working with models, choosing models, or you don't have to create models from scratch. Already, a lot of intelligent people have done this, so you don't have to reinvent the wheel. But you just have to decide which model fits your data best, and you have to also understand the models a little bit better so that we can take decisions more intelligently. So when S tends to infinity means the denominator is very large. So what then happens is that this entire thing tends to tends towards zero, right? When you have a very large denominator, becomes the overall thing becomes much smaller in size. So that's why the maximum revenue attainable is A, right? So that's a simple mathematical logical deduction. And B, by the way, this is taken from the concept of half-life. So the spend level at which the revenue is half of A, roughly or approximately. Okay, so you can see that um, if you just put it, is half of it. So if you just put it S here, right, then it becomes A into S by 2S, right? So it becomes A by 2, right? So that's why you can say that this corresponds to that specific ad spend, uh, which for which the revenue becomes half of it. But that's just a mathematical way of looking at it. The important point is to understand the trend that you get from it, and the trend is that uh, is something which we have already seen, that the revenue sort of tapers off as the spend increases. There are different types of diminishing returns models. This is just one, and in fact, if you just look it up, you'll see that this is taken from pure science. So it's obviously not just in the context of business economics that these models are used there. They've been used previously in many other places. Here's another one, exponential response model. There's an initial rapid growth that slows down as spend increases. So there's a similarity again with the diminishing returns model that we had just seen. So again, RS stands for similar things. Maximum achievable revenue is still A, and the rate of revenue growth, uh, you know, um, is actually determined by this factor B, and this actually also, is an indicator of how quickly this particular model is going to saturate. Then there is the power law model, which captures scale effects pretty well. When the initial ad spend has a disproportionate impact on revenue, but again returns diminish rapidly afterward. So these are not strictly diminishing returns models, but they all sort of are around the similar sort of space, as you can see from this curve here as well, from this part of different curves. So you see the power model here being plotted by the blue line, and it's also somewhat similar, as you can see, and because of the nature of the equation, very simple equation. Then there's this factor, the exponent, which determines the degree of diminishing returns. The factor lies between 0 and 1. So it's between 0 and 1. That is why it's diminishing. Otherwise, it will not be diminishing, right? It has to be less than 1. Now, there's another one. This is the logic curve or the S-curve model. And there's a revenue and spend, maximum revenue again, which is A. And see, the steepness of the curve is determined by a factor B. And then there's an inflection point at which the spend level where the growth is the fastest. Okay. So these are the important parameters of this equation. This again is a very useful response curve model. So these are just some. There are so many others. There's a hill function, and then there are, just so many kinds of models which you can use. You just have to see which one fits your data the best. All right. So if you want to learn how to do curve fitting, There are two resources that I would definitely ask you to explore. First is the Desmos calculator. And I will just turn on a couple of things here and you'll immediately see why. It's so cool. So what it does, it gives you visually a live demonstration of how for different values of the parameters, your response model will change. Okay. So this is basically the Metten, I think it's the Michelson-Metten equation again. I'm getting the name right. Yeah, the Michaelis-Menten model. So you see, this is the one. This is actually the same equation here. This AS by B plus S, everything has to be in terms of X and Y here. So AX by B plus X in Desmos. And for different values of B, which are ranging from -10 to 10, as you can see, and you can actually decide also the ranges for yourself, how this model is going to look like, right? And then you will see that, these curves are actually changing. So if I actually also put it -20, it's going to look more symmetrical once more. Right. So you'll see, how these are changing for different values. And both of these are the asymptotic curves. We saw the diminishing return curves, right? And yeah, since it's actually varying from -20, from minus to plus, that's why it's on either side, like this way. Okay. So that's the whole point of this sort of a really nice graphing tool like this, where you can visually literally see how these different things, how these different models are going to vary for different parameters, and this gives you a very nice indication of what you are really dealing with. Okay, so suppose you put in get rid of all of this, and you say, okay, all I want is say 2x plus 3. So you can see the response curve model, which is the linear model here, which is in this format. You can already see, how it is getting generated. You can put in any equation you want. So let's say it will be this one, 2 into, I'm just going for the easier one so that it's faster. And then you have to put in some sort of sorry, it's going to be less than 1. So there you go. That's one of the response curve models here. So if you look at the right side of it, of this, because it's bounded in two directions. So, but if you look at only the positive side of the x-axis, you actually see another response curve model here, which has a similar sort of thing to the diminishing returns model, right? So that's the thing. I mean, if you suppose put in b here, and then you add a slider for b, and then you say, okay, this varies between 0 and 1, remember? So you say that, okay, this will be from 0 and this will be to 1. You can also add the steps at each step of the iteration and by how much it's going to change. You can then have the slide, turn on the slider for B, and it's so beautifully going to give you a visual demonstration of how it's going to vary for different values of the parameters. So this I actually use a lot when I have to decide on what kind of response models I should be going for. But if it's a little too mathy for you and you want to dive right into just using a block of code and get it done with. Now, the reason why I'm talking about code here is because fitting is itself a fairly mathematical process. There can be a very sort of dumped down manual method, which is also good sometimes for quickly doing things. So take any random values for these constant values here like a and b, but they're very, very important values. They actually determine the nature of the model. But take some values like that, take them within uh, the ranges that are, you know, that actually make them the models that they are. For instance, you have to take it between 0 and 1 for it to be a diminishing model. And take that, and then you try and fill in with these data points that you have in your actual data set, and then see whether or not, take it for all the data points or not. If not, if that's not practical, then take it for some of them, and then see if it actually fits the model or not. So that can be a manual method, and if you see that it's getting a good match, that by putting in the values on the right hand side, you're getting back the revenue, which is here. And it matches in most of the cases, or there's a very close match, then you can say that okay, it's uh, it's a good match. But it's a manual method. It's not a very strong method. A much stronger, much more scientific, proper method is the way of using, code. So this is basically an online book. Has a lot of different topics, but as you can see, the parameterized S curves, and so this is using the logistic function. For instance, we already saw the logistic function. So you can see there's a section here for curve fitting. So what it does, it first generates some data points from the logistic function. So you can see that it generates some random points here. This is Python code, and this is the generated S curve with, and it has introduced some noise and all. So the way this has been done here, is that it's used the logistic function, and it is between -6 and 1 at steps of point 0, point 0.1, and it has generated this logistic function here. And once that has been done, it's going to now try and fit the curve, okay? And it's going to try and fit the curve over a proper logistic function, where the logistic function has been defined separately, okay? And so there you go. So this is, and then you actually, plot the actual y values and the predicted y values, and then you overlap them together. Okay, so that's basically a visual curve fitting, and you see they fit so well. The noise was deliberately introduced into the data, okay, so as to so as to basically make it a little bit realistic, right? Otherwise, the curve fitting will look like they're just absolutely one over the other. But yeah, this is just an illustrative example. The whole point of it is that you can do so much once you have access. As you can see, this is not too much of Python code. You just have to jump into any Python environment and you can get started. Yeah, I'm comfortable more with Python. That's why I gave the example of Python. You can try anything else. But my point is curve fitting in itself, or response curve building and validating, or all of that is not necessarily a absolutely simple method where you can completely avoid any kind of code or any kind of more mathematical approach. But as I said, I mean, there's this manual approach which I just hinted at. That's also worth a shot if you want to just, try some back of the napkin math, as they say. So this curve fitting, by the way, is also done using Python, as you can see for channel 1. And this is the method that you should be adhering to when you're taking decisions regarding the investment of the next dollar, or especially because it makes a bigger impact, and it's more significant when you're trying to invest something of the magnitude of say $1 million. So yeah, I mean, hope this was useful, and yeah, do let me know in the comments if you have any questions. And I'll see you in the next video. Thanks for watching.